This is Daniel Coosbury, and in this video we're going to look at how to do a one-sided hypothesis test for mu when we don't know the value of the population standard deviation sigma. So the context that we're in is that we have some population and we're interested in estimating what the value of the population mean is, but we don't have all the population data, so we'll need to end up taking a sample from that population, nice random sample, and we're going to use things from that sample to estimate what mu is. Now, this is distinct from the situation where we do know what sigma is, because now we don't. This is probably a really common situation. If you don't know the population mean, most of the time you're not going to know the population standard deviation either. And so we have methods for estimating what mu is and testing for hypotheses about what mu is using the sample mean. And we're also going to need to use, in this case, the sample standard deviation, S. This isn't writing, S. So we're gonna have a method that uses both X bar and S because we don't have sigma. We're gonna use S instead. And so I'll show you how that works through a couple of examples. Or really, this is just one big example, I suppose. So here we have a company that wants to improve sales. Past sales data indicate that the average sale was $100 per transaction. After training your sales force, recent sales data taken from a sample of 40 salesmen indicates an average sale of $115 with a standard deviation of $21. And the question we want to answer is, did the training work? And we're going to use a hypothesis test to try to answer this question. So just to kind of set this in a hypothesis testing context, what we know already is that in years past, I guess in the last few years, or however long this was, the average sale data was $100 per transaction. And then you do some training, and your goal of training would be to increase sales. It wouldn't be to like decrease sales. So the only reason you would, or the result you would want from your training, or we could define the training working as my sales average sale went up from $100 to maybe $101 or $150 or something nice. So what we're going to do is we're going to state the null hypothesis. And let's let the null hypothesis be, well, it always has to be mu is equal to something. So let's let it be mu is equal to 100. The null hypothesis would be, no, the training didn't work. The mean stayed the same. The alternative hypothesis, on the other hand, is going to be that it increased. So this is I think you should see that it's a one-sided test because if we have to set mu equal to something, 100 is really the only number we can use. We can't use this 115 because this is X bar. This is the sample standard deviation because it's in the same sentence as the sample mean. But since we have to do the null hypothesis is mu is equal to something, then the alternative hypothesis will be, yes, the training did work and our mean is bigger than 100. So let's assume the mean equals 100. And if that's not true, we'll conclude the mean's bigger than 100. We're going to use a alpha is equal to 0.01 significance level. So alpha is equal to 0.01. And this is the test statistic that's unique to the situation where we know mu. I mean, we don't know mu. We're estimating for mu and we don't know what sigma is. So when we're estimating for mu and we don't know what sigma is, we have to use the t-distribution. This is the exact same, for the exact same reason. We have to use the t-distribution for confidence intervals when we're estimating for mu and we don't know what sigma is. In the same way, we've got to use it for hypothesis testing when we estimate for mu and we don't know what sigma is. So when this little guy, the sample standard deviation comes into play, we got to use the t-distribution. So the test statistic we're going to use is t is equal to x bar minus mu divided by s over the square root of n. And that follows a t-distribution with n minus 1 degrees of freedom. So this n minus 1 is the degrees of freedom, the sample size minus 1. The t just stands for the t-distribution. So we're using this guy, the test statistic, which is x bar minus mu under the null hypothesis. This will be 100 in this case. The sample standard deviation and over the square root of n. And once we get this statistic, we're going to use the t-distribution rather than the standard normal distribution to do things. So we're using the t-distribution with n minus 1 degrees of freedom. So let's go get some numbers. Our sample mean was 115. Our sample size was 40, and our sample standard deviation was 21. So in this example, t is going to be equal to, x bar was 115. Mu naught was what mu is equal to under the null hypothesis. S is equal to 21, so that's our sample standard deviation. And our sample size is the square root of 40. I'm sorry, the sample size is 40. We're going to take the square root of the sample size, which is the square root of 40. So you do this in your calculator, and you'll get your test statistic. It should be some number. Hopefully it's between -5 and 5 if we do it right. So when I do this in the calculator, I like to do it all at once so I don't end up rounding things. So when I do it in the calculator, I like to put parentheses around the numerator and then divide, and then put parentheses around the denominator as well. So 21 divided by the square root of 40, and then close parentheses. So you see I put parentheses around the numerator and parentheses around the denominator, and then nothing bad happens. I should get a number that's probably between -5 and 5. Oh look, 4.52. We'll round it to 4.52. So that's between -5 and 5. It could be bigger, it could be smaller, but usually they're between, like, unless the data is really extreme, you're looking for something between -5 and 5. It's a good way to know you didn't mess up the calculator thing. So our test statistic is 4.52, and this follows a t-distribution with 39 degrees of freedom. So n minus 1, n's 40, subtract 1. So a t-distribution with 39 degrees of freedom. We're going to use that to compute some probabilities with this guy, the test statistic. So let's start out by doing the critical region method. So we could do this, or we could do the p-value method. There's no reason to do both, but the idea with, I'm showing you both methods anyway, so we can use the critical region method to draw a conclusion, or we could use the p-value. So we'll start out by doing the critical region method. And for a right-sided test in which our alpha is equal to 0.01, we're going to be asking this question. If the mean is really 100, meaning it didn't go up, the training didn't work, is it unusual if our test statistic t is at least as extreme as 4.52? Now, in the one-sided, the right-tailed test, we by extreme we mean large. So if you've seen a two-tailed test, extreme could mean small or large. But when we're doing a right-tailed test, we mean, is it unusual if our test statistic is at least as big as 4.52? So what that means for the critical region is, imagine that we have a significance level of 0.01, which means that if something has a probability of happening that is 0.01 or less, we're going to call that unusual. So in this context, since alpha is 0.01, that's going to be our cutoff for unusual. So if the chance of getting something at least as big or bigger than 4.52 is less than 0.01, we're going to call that unusual. Now, if you look at our curve, 4.52 doesn't even show up on here. Well, so I'm just going to have to draw it out. There's like almost no curve. There's almost no curve here. See how close the blue curve gets to the black line right here? It just stays there, which means there's almost no area under the curve, which probably means that this is a really extreme value. So any probability you compute out here is going to be teeny, teeny, tiny. But let me show you how the critical region method works. So we're going to reject anything that has a chance of 0.01 happening or bigger. I'm sorry, a chance of happening of 0.01 or smaller. So anything smaller than a 1% chance. So I'm gonna split up my curve into the lower 99% and the upper 1%. So this is the upper 1%, and it's gonna be this little tiny red sliver. And what I need to find for the critical region method, this little tiny one, see how, so that's roughly 99% of the area. That's like 1% of the area. What I need to find for the critical region method is, what is this cutoff? What's this cutoff that will give us the upper 1%, that'll like separate the 99 from the upper one. So we're going to call this t.01, and I need to find out what that number is. And remember, I'm using a t-distribution with 39 degrees of freedom. So for this, I'm going to go into my calculator and use the inverse t command. So I go to second vars and use inverse t. And I'm going to tell it the area to the left is this 99%, 0.99. The degrees of freedom are 39. And hopefully it gives me something between 2 and 3. It might be bigger than 3. I don't actually know off the top of my head. But we should get something. Okay, yeah, so I kind of guessed right. It's 2.43 is going to be what we round that to. So let's call that 2.43 is this number right here. So let's back up and say, what is this number? Well, first off, it's called a critical value. It separates the common 99% with the upper extreme 1%. Critical value. That's what that is. And so this red region is called the critical region. Let me write that in red. That's the critical region. And that's just, we'll call that the regular region, just the regular 99%. This will be the upper extreme 1%. And so the way this method works is if our test statistic falls in the red region, we're going to call it unusual. The chance of it happening is under 0.01. And obviously it does. The test statistic falls right here, 4.52. So it's in the critical region. And because it's in the critical region, we're going to say it's rare, it's unusual, and we're going to reject the null hypothesis. So this is a really extreme value. And if it is really extreme, this is probably wrong. We're going to say that this hypothesis mu is equal to 100 is wrong because this is super extreme if that's true. So let's look at the conclusion. We marked off the critical region such that any t value that falls within the region has less than a 1% chance or less of occurring. Since t falls within this critical region, the probability of its occurrence is less than 0.01. So we will conclude it is unusual to get the statistic if this is true. Remember, this is H naught. So if H naught's true, this is super rare. So we're going to say H naught is not true because this is super rare. So we're going to reject H naught because this is unusual, because 4.52 falls in the critical region. So if you're looking for a nice hardened rule, since this is true, we reject H naught. If 4.52 fell in that left side, that 99%, we would fail to reject H naught. But since it falls within the critical region, we reject H naught. So if you're looking for a rule that works for every hypothesis test, if the test statistic falls in the critical region, reject H naught, just period end. So if you set the critical region right, if you found that cutoff, the cutoff, this case being 2.43, so everything bigger than that, you reject. That's the rule. If it doesn't fall in the critical region, you don't reject. So our conclusion then is we have sufficient evidence to reject H naught and conclude that the average sales this year was greater than $100 per transaction. That is, we can conclude that the training was successful in increasing sales revenue. So this second sentence is my not statistical sounding one, but it's a good conclusion that people can understand who haven't taken a statistics class. Great. So let me show you the p-value method. It's related to the critical region. It's the other way of doing this. So we're still trying to answer this question. So back up like 2 steps. We haven't drawn a conclusion yet. We just got our test statistic, which is 4.52. That should be a 2. And we're asking if mu is really 100, is it unusual if our test statistic is at least as large as 4.52? And on our graph, we know that 4.52 is like way out here. So this is 4, this is 5, and 4.52 is like right here. And the question is, what's the probability in this distribution, which this is a t-distribution with 39 degrees of freedom, what's the probability of getting some number way out here or bigger? What's the chance of finding this little tiny red sliver right here? And you can look at that and say that's a super small sliver. The probability of getting that is teeny tiny. So it's probably unusual. It is unusual, but we still need to find the p-value. So the p-value is just our proof that it's unusual. The p-value is going to be equal to the probability that t is at least as big as 4.52 under the t-distribution with 39 degrees of freedom. So for that, we're going to use a function under the calculator that you may not have used before. It's called TCDF. And what TCDF needs in order to work, I think it needs 3 things. Hold on just one second. TCDF works a lot like normal CDF. It needs a left side, a left boundary, a right boundary, and it needs your degrees of freedom. So normal CDF gives you areas under the curve. TCDF will also give you areas under the t-distribution. We're in the t-distribution. And you've got to tell the TCDF your left boundary, your right boundary, and your degrees of freedom. So I can go ahead and fill this in. This is 39. For the left and right boundary, we're finding the area of the red sliver. So your p-value is equal to the area of this red sliver, which is also the probability that you get something that big or bigger. So the p-value is the probability you get something that big or bigger. It's that area right here. So let's put off boundary markers for the red sliver. You're going to start at 4.52. That's the left side. And the right side, this goes on forever. This goes on all the way to positive infinity. It goes on forever and ever. So let's just put a big positive number there like we would with normal CDF. So this is how you find the area under the curve for a right tail. There's your starting point, and it goes all the way to positive infinity. If you're finding this confusing, the picture is the way I get to do this right. Is I can see the sliver, I see the left side, I can see it goes on forever. My degrees of freedom is that. So TCDF, let's see if I can make this a little bigger. TCDF is under second vars, and it's down here. So there's normal CDF. TCDF is just a little bit lower. Your left side is going to be 4.52. Your right side is going to be 9999999. Your degrees of freedom is 39. So that's it. That's exactly how I wrote it. If you got an older calculator, you write it the way I wrote it. And you hit paste, hit enter again, and you get something microscopic. So this is 2.81 times 10 to the negative 5. So on my, well, maybe I should go a few more decimals. Let's do 2.81. That would round up anyway. So this is how you could write it. It's 2.8100 times 10 to the negative 5, which is equal to 0.0000281, which with the p-value method, all you have to do is compare that to alpha is equal to 0.01. So like you can be as precise as you want to be here, but at the end of the day, you're going to see if this number is bigger or smaller than 0.01. And of course, it's microscopic. So we can draw the same conclusion that we can with the critical region method. So the p-value is this, which is the TCDF, which is 0.000028, which is far less than alpha is equal to 0.01. So we can say that if mu is 100, meaning the training didn't work, the probability we take a sample with a mean at least as large as 115 is this number, which is microscopic. So we're going to reject H naught because, well, this is one way of saying it. We only have if we reject H naught, we only have a tiny chance of being wrong. In other words, we're not wrong. But we are going to reject H naught because our p-value is 0.000028, which is less than 0.01, which is alpha. So the p-value is less than alpha, so we reject H naught. So if you're looking for a nice rule, this is the rule. If the p-value is less than alpha, reject H naught. If it's bigger than alpha, you fail to reject H naught. So I have the same conclusion here. We conclude that the sales, the average sales has increased since last year, and that's because of the training. So we conclude the training was successful in increasing sales revenue.